That's my sound. Yeah, so just remember to stick around and we can, I'll make sure to try to solve your issue. All right, so we were talking about vector addition and subtraction last time on Wednesday. And so I showed you a way that you could calculate the sum of two vectors by just putting the tail of one on the head of the other, and you could do the same with subtraction by multiplying by -1 first, which flips the vector. Now, vectors are a mathematical tool, so we should be able to calculate things like symbolically using like algebra or arithmetic and things like that, rather than just graphically. Like, you don't see all of these highfalutin mathematicians drawing pictures all the time of vectors, like they're just doing calculations, right? So to do so, I'm going to introduce this idea of vector components. So vector components are going to be the things that allow us to calculate things symbolically rather than graphically. So first let's give a quick example. So if I were to ask you, what is the magnitude of, say, the vectors, or of, say, the vector a plus b, where a is some vector and b is some vector. So I'm asking you what the magnitude is of the sum of the vectors. Well, what you could do is you could use trig. And so you would say maybe a is this vector, and so you would put b over here. So maybe this is b and this is a. Then the vector a plus b would be the vector that forms a triangle with the other two, right? So it would look something like this. And now you could use geometry and some basic trig to establish what the magnitude of a plus b is. So we would have that the magnitude of the vector a plus b, remember these two vertical bars on the side indicate that we're taking the magnitude of the thing that's inside of it. So a plus b is a vector. So the magnitude of this vector squared, this is just a basic like triangle fact, is the magnitude of the square of its side lengths, which have length a and b, the sum of the square, minus this factor here, the magnitude of a, times the magnitude of b, times 2, times cosine of the angle between them. And so you could go and you could do this computation, but you don't have to. So it's not particularly convenient to do so. And I mean, don't worry about this formula because we're never going to use it. Instead, we're going to leverage some of the useful facts about vectors. So first, and we're going to do this so that we can quote unquote distance, pun intended, ourselves from geometry. So first, recall that, or maybe recall is not the right word, but note that any vector can be replaced by the sum of two other vectors. So the example I'm thinking of here is, let's say you have a vector like this, right? Well, you could just as easily replace that with a vector like this and a vector like this, and then add those two vectors together, and that will give you the original vector back, right? So this is always doable. You give me a vector, I can give you two vectors that add together to give you that vector. And in particular, those two vectors can be perpendicular if we so choose. Also, another fact is that it's easy to add parallel vectors. So if I hand you two vectors that are parallel, i.e. pointing in the same direction, then it's easy to add them. So if you have one vector like this and you're adding to it a different vector with a different magnitude but in the same direction, that's just this vector attached to this vector, which is just, it points in the same direction as the original two vectors, and all you do is add the magnitudes. And that gives you the new magnitude. And then the third fact doesn't really have to do with vectors, but it's a fact of geometry that trigonometry is easy with right triangles, right? If you want to compute the length of a hypotenuse or the length of a third side, you just use the Pythagorean theorem, right? You know, a squared plus b squared equals c squared. So these three facts combine to give us, come on, erase, to give us the tools to easily handle vectors in sort of a like algebraic symbolic type way. So the way that we do this is we pick two or more, if we're dealing with higher dimensional vectors, pick two or more perpendicular axes and we break up each vector in our sum. So we're talking about how do you easily handle adding up two vectors. You break up each vector into the sum of vectors, pointing along those axes. So the key here is this picture. So we would have this vector here, maybe A, and then we break it up into two vectors. Maybe we call it A1 and A2. And so if our axes were like these axes, you know, just standard Cartesian axes, then those vectors would, like the vector A1 would point to the right, the vector A2 would point up. And so they would be pointing along those axes. Now there's a caveat here. They can also point like in the opposite direction. They could have been pointing left or down, and that's equally okay. And so we give a name to the lengths of these vectors. So the lengths of those vectors along the axes are called components. They are the components of the vector. So here's a picture that'll be pretty detailed in. So let's say we pick our standard axes, x and y. And we can do that. And let's say that we were given this vector, say, let's call it A again. So remember, you can always move where your vector is. You can always move the tail of your vector. So I'm just going to take this vector and move it over here to the origin. Because you can always do that, right? So the point is that I could break down this vector into a vector that points up along the y-axis. I'm going to call that vector, sorry, let me be a little, oh boy, maybe a little bit more clear. So there is some vector that points just upwards and doesn't have a length. That would be a unit vector. Let's call that y hat. It's just a vector that points in the y direction, but it has unit length, right? That's what this little hat means unit length. And then there's a little vector in the x direction that points in the x, or there's a vector x hat, points in the x direction, and has unit length. So what we can do is we can figure out the lengths of, or we can figure out what the component vectors are, the components are of this vector here, A, in each of these directions. So this vector, this taller one, that vector would be the vector that we call AY in the y hat direction. So the reason why we care about the lengths of the vectors along the axes is because you can just multiply the length of that vector, or you can multiply that component by the unit vector in the direction that it points. So this vector, AY times y hat, points in the direction of y hat, and then has length equal to the component AY, which is just the length of A in the y direction. Similarly, we could do the same thing for the other component. This vector here would be AX in the x hat direction. And so then what we can say, because we can always break it, or all we've done is we've decomposed a single vector into the sum of two vectors. In this case, we have A, the original vector A is equal to AY in the y hat direction. Sorry, let me write it in the correct order. AX in the x hat direction plus AY in the y hat direction. That should be fairly clear. This is the vector that points from here to here. this is the vector that points from here to here. And so when you add them together, tail or head to tail, you get the original vector A. And so the numbers AX and AY, those are the components. Those tell you how far does the vector go in that direction? How far does the vector go in that direction? And then X hat and Y hat, those are just the actual associated directions. Remember, unit vectors are associated to directions because they don't have a meaningful magnitude. They have length 1. So now let's assume that the vector B that we want to add to A, let's just say that it has unit vector, or that it can be broken down into bx, x hat, plus by, y hat. And this is always doable. For any vector, for any two-dimensional vector, you can always break it up into components like this. So now, we can now manipulate the vectors algebraically. So we know that it doesn't matter what order you add things in, right? So we have A plus B. This is equal to, well, A is AX in the x hat direction plus AY in the y hat direction. And B is BX in the x hat direction plus BY in the y hat direction. Now, these 4 things, those are all vectors, right? So they will add together like vectors, but we can just rearrange things and see if we can simplify our work for us. So addition is associative, that's just a true fact. So we can, we can rearrange these parentheses and reorder things. So this is equal to AX plus BX in the x hat direction, right? So all I did was I combined these 2 terms and then factored out the x hat. X hat it's just a symbol that you can factor out here. We're just treating it like a symbol, plus AY plus BY in the y hat direction. Yes, so 2 vectors do have to have the same units because it wouldn't, like, it's almost common sense, but it wouldn't make sense to add like 5 feet to the right to 3 meters per second. Just like how you can't compare 2 symbols or two quantities that have different units, you can't really add them or subtract them either. Because if you could subtract them, then you could compare them. Like, for example, 3 meters is less than 5 meters because 5 minus 3 is greater than 0. So that's a way to get a comparison from a subtraction. So if you can't compare them, you certainly can't subtract them. We will get to dot and cross them soon, but for addition and subtraction, you certainly cannot add them if they have the same units, right? It's for the same reason that you can't compare them. Right, so what this does is it gives us the components of the resulting vector, right? Of the vector that results from adding the 2 vectors A plus B. So now, if we were to plot this, let's say that A is this vector, and say B is this vector, well, this distance here would have been BX, this distance here would have been BY, this distance would have been AX, this distance would have been, this distance would have been AY. So the resulting vector, this vector here, sorry, I know it's getting cluttered, A plus B, well, it would go AX plus BX units to the right, and it would go AX plus BY, or AY plus BY units up. And so the resulting vector would have sides AX plus BX and AY plus BY. And so now we can ask the question, how do you find the magnitude? What is the magnitude of, say, A? Let's just talk about A for now. Let's not talk about the magnitude of A plus B, because that's just a generalization. The magnitude of A, if A is just this vector, has length AX here, AY here, well, now you can use the Pythagorean theorem, because this is a right triangle. So the length of A is just the square root of AX squared plus BX, or plus AY squared. And similarly, you could see the length of AX plus BX. It would be the square root of AX plus BX all squared plus AY plus BY all squared. So we've been using these unit vectors, this x hat and this y hat, as just like things that you can move around, like as just abstract symbols. But it's useful to actually understand what the unit vectors mean. The unit vectors, the unit vectors contain information only about direction. The point is they don't, like, they're just there to be the part that gives direction to a vector. So a vector has a magnitude and a direction. The unit vectors are just there to make sure that the parts that we're talking about are still vectors. They contain information about the direction that a given vector is pointing in. And they tell us how much, or they tell us what direction we are trying to measure the component of, right? So if we were just given this vector without, like if we were just given this random vector, if you want to figure out what the components are, you first have to tell me what direction you're measuring the components in. Like I could be measuring the components in a tilted axis system, right? And so that means you'd have to give me a vector. And the vector that you would give me would be a unit vector, because it doesn't have any bias to it besides just the direction. It doesn't have any magnitude. So unit vectors are particularly useful because they can tell you about direction without having any more bias or anything else attached to them. Now, in this case, the case that we've been talking about, it's the components that carry information about the length, or about, carry information about length. And by the way, components can be zero. Like it's possible to have a vector that has a zero component in one direction and a non-zero component in the other direction. Now, there's a conventional naming system for the standard unit vectors. We call the unit vector in the x direction. That's typically called the vector I, and we replace the dot with the little hat. And then the y unit vector, we usually call j, again with a little hat. And then the z unit vector, if we're, say, working in three-dimensional space, which you could be, we call that k with a little hat. And so you only have the z unit vector if you're working in three-dimensional space, but we live in three-dimensional space, so it's not surprising that that will come up sometimes. Right, so that's how you can symbolically handle the addition of vectors. Like rather than having to just draw pictures, all you have to do is figure out the components of the two vectors you're worried about in some axis, some set of perpendicular axes. You can choose which axes those are, but the standard ones are pretty good. And then just add the components up for each direction, and that will give you the final vector. And if you want the magnitude, you can use the Pythagorean theorem. If you want to figure out what direction it's in, you can use some trig to figure out the angle that it makes with say the x-axis, and so on. And you don't have to worry about drawing things anymore. Now, that's addition, that's subtraction. Subtraction will work the same way, by the way. You just subtract components rather than add them. Multiplication gets a little bit trickier. So let's talk about multiplication of vectors. So we already know that you can multiply a vector by a scalar. Now, I don't think I'll actually talk about this. So yeah, so if you want, so we know that multiplying a vector by a scalar, by just a number, all that does is it stretches or shrinks the vector, right? So if you have a number, say, little a times the vector capital A, then if we break it up into components, this is just a times ax, I hat, it's in the x direction, plus ay, j hat. I'm going to assume it's a two-dimensional vector. And so this is just the vector a times ax in the I hat direction, plus a times ay in the j hat direction. And so all you're doing is you're just stretching or shrinking each of the components by the same amount. And so that keeps the direction the same, but it changes the length. Now, there are other ways to multiply. You could, for example, try to come up with a way to multiply two vectors. So unfortunately, you cannot just multiply vector components. Like, the way that we do multiplication has a well-defined, rigorous definition, and so it shouldn't matter what choice of coordinates you're using. And so if you just multiplied vector components, like if you just said, well, the vector a times the vector b was ax times bx in the x hat direction plus ay times by in the y hat direction, and so on, that would not, or the resulting vector you would get would depend on what axes you had chosen. And the axes we choose are arbitrary. You can choose whichever axes you want. So you really don't want to do that, because it tells you more about what axes you chose and less about the fundamental objects that the vectors are. So that's not a sensible way to multiply vectors. However, there are two unique ways that we can multiply vectors in 3 dimensions. And these ways of multiplying vectors do not depend on the choice of axes that you make. Now, I say that there are 2 unique ways to multiply vectors in 3 dimensions, because in anything besides 3 and 7 dimensions, there's only one unique way to multiply vectors, actually. It's a weird quirk of, anyway, I'll just leave it at that. Maximus, so you sent me a question privately, but I think that this question is public, so I'm gonna read it out. So Maximus asks, if we have a number times a vector, that's just a scalar. But if we have a vector times a vector, then it's a dot product, right? No, so a number times a vector is a vector. This thing here, this is a vector. It's just a vector that's been stretched. A vector times a vector has, in 3 dimensions anyway, has 2 distinct ways of multiplying. So I will go over the 2 ways, but first I want to give some justification. So first, let's talk about why we might want to multiply. So the first, so I'll just give an example here. If you apply a force to an object, at an angle, no, apply a force to an object. Yeah, apply a force at an angle to an object that's moving. And I'll draw a picture in a minute. That is being pushed. What happens? So we haven't talked about force and work and all of that business yet, and we will. But you guys can hopefully understand the idea that if, say, you have a box on the ground, if you try to push it downwards and to the right, it'll move to the right, but it won't move as fast as if you just applied the same magnitude force directly to the right, right? In some sense, some of that force that you're applying is wasted, right? Especially if it covers some distance. Like some of that force is wasted. Now, in this case, there are 2 vectors present. There's a vector that goes, there's a force vector that tells you how strong you're pushing with and the direction that you're pushing in. And then there's also the displacement vector, which basically tells you what direction did the object go in and how far did it go. So if those 2 vectors aren't aligned with each other, you're kind of losing some force, right? And so you might want to come up with a way, and it turns out that this will be useful, you might want to come up with a way to account for that when you're multiplying those 2 quantities together. And we might want to multiply those 2 quantities together because clearly it takes more force to go twice the distance than it does to go half the distance, right? So in some sense, those 2 things should, it'll take more energy to go twice the distance than to go half the distance. And so in some sense, there should be some relationship between a displacement and a force and then energy. And that turns out to be the case, and we'll go into more detail on that later. But the point is one way that we can multiply vectors kind of accounts for this loss of, for this loss of the 2 vectors that we're multiplying together not being perfectly aligned. So to capture this phenomenon, we introduce the we introduce this notion of the projection of one vector onto another. So the way to think about the projection of one vector onto another is to think of it as the length of one vector casting a shadow over the other. So I'm going to put that in quotes because it's not quite true, but it's a good intuition. So the picture here is, let's say you have a vector like this. And well, maybe I'm not going to give it an egg because it doesn't really matter. Let's say you have another vector, and we can always put their tails together because that's just, you can move tails around however you want. Another vector that's up top. There is, like, they're not pointing in the same direction. There's some relative angle between them. Let's call that angle, say, theta, right? So the projection of, say, I'll call this A and I'll call this B now. So the projection of A along B would be the length of the shadow that A casts in the direction of B. So that would be this vector here. So, or sorry, not vector, it would be the length there. So this length here is the projection, or it's the projection of A along B. I'll just put that down here. Importantly, the projection is a number, not a scalar, or not a vector, it's a scalar. So the point is to multiply two vectors where some of it's wasted, we can multiply the length of one vector by the projection of the other. And so what this does is it basically says this type of multiplication is greatest when the two vectors are lined up perfectly, because then the projection is always shorter than the actual magnitude of the vector it's coming from, right? But if they're lined up perfectly, then the projection, the length of, or the projection is just the length of the original vector. So in this sense, this kind of accounts for that waste, like that you're wasting some of one vector because it's not going in the direction of the other vector. And it's a useful concept. And so we would notate that A dot B. So this dot, it's not just the standard multiplication dot, it's a particular vector operation that we use specifically for vectors. And so this would be equal to the projection of A onto B times the magnitude of B. And so in this case, this is a number, not a vector. It's a scalar, right? So geometrically, you could just work out the geometry. If the angle is theta between them, then the number that A dot B is, that is just the magnitude of A times the magnitude of B times the cosine of that angle. And I challenge you to go home and work that out, verify that what I just said is true. And this type of vector multiplication we call it the scalar product or the dot product. And I'll use those interchangeably. And so if you were to read this symbol, like if you have A times B, you would just read this as A times B. If you were to read this string of symbols, you would say A dot B. That's the standard language that's used when we're talking about the scalar product or the dot product. It's called the dot product because it has a dot. Yeah, Yeah, so remember the bar on either side means the magnitude of the thing inside. So yes, so A with two bars with a bar on either side and a vector arrow means the magnitude of the vector A. Yeah. All right, so I've defined this dot product for you, and now there are just some properties that I should probably tell you about, properties that the dot product has. So just as regular multiplication is associative, it's commutative, meaning you can change the order, like 3 times 5 is 5 times 3. You can rearrange parentheses with multiplication. It distributes over addition. We can ask whether or not these properties also hold for the dot product. So the first property that I should tell you about is that the dot product is commutative, meaning it's the same regardless of what order you write it in. You'll get the same answer. Similarly, or not similarly, there's another property, which is that a vector dotted into itself is just the magnitude of A squared, right? Because it's A times the magnitude of A times the magnitude of B, but B is A here, times the angle between them. But the angle between a vector and itself is 0 degrees, and the cosine of 0 is 1. So this is just the magnitude of A squared. And so sometimes I'll use this notation where I'll just write A squared. Like when it's clear that this goes back to that whole business of sometimes I'll just drop the arrow to indicate the magnitude. And so this is just the magnitude squared. It's just the notation that I'm using. This is notation. Another property. We can talk about the dot product of unit vectors. So the unit vector I points in the x direction, has length 1. Dot itself, well, we know that any vector, including unit vectors, dotted into itself, we know that's just equal to the magnitude, right? It's equal to the magnitude of the vector. What's the magnitude of a unit vector? It's just 1. So I dot I is 1. Similarly, we can work out what I dot j is. So I points in the x direction, j points in the y direction. So what would I dot j be? Well, using this formula, it would be 1 times the cosine of the angle between them. Now, they're at right angles. One points in the x, one points in the y. So the angle between them is 90 degrees. Cosine of 90 degrees is 0. So I dot j is 0. And you could make similar arguments for I dot k. That's also 0. Then we have that j dot j is 1, and j dot k is 0, and of course k dot k is 1. So unit vectors are really nice with regards to scalar multiplication. If you dot them into themselves, you get 1. If you dot them into the other unit vectors, you get 0. It's an easy thing to remember. Fourth property of the dot product is it distributes over addition. So the point is if you have A dot B plus C, A dot B plus C, so B plus C is a vector, so you can dot A into it. This is equal to A dot B plus A dot C. It distributes, unsurprisingly. And so it turns out, maybe it's not that it turns out, this is just a true statement. We can use this dot product to extract components of vectors. And the reason we can do that is because of this property, or property C and property D. So let's say that A is AX in the I hat direction plus AY in the J hat direction plus AZ in the K hat direction, right? That's fine. It's just some vector with some components in those directions. Then, well, we can just ask, what is A dot I equal to? Well, A dot I is AX in the I hat direction plus AY in the J hat direction plus AZ in the K hat direction, dotted into the I hat vector, right? And we know that the scalar product, the dot product, distributes over addition. So we could distribute this inside to each term, right? And so this is equal to AX times I hat dot I hat, and we know that that's equal to 1, plus AY times j hat dot I hat, sorry, dot ay times j hat dot I hat, that's equal to 0. And then az is k hat dot I hat, which is also equal to 0. So this whole thing gives us ax. So if we're given a vector, we can compute its components by dotting it into the various unit vectors. So if you wanted the y hat, or if you wanted the component in the y direction for this vector, you would dot it with the j hat vector, and that would give you the component in the y direction. Also, we can compute, or we can calculate a dot b directly using components, rather than using the formula, rather than saying it's, rather than using the magnitude of a times the magnitude of b times cosine theta. We don't have to use that formula anymore because we can break them up into components. In this case, I'm just going to assume that they are two-dimensional vectors, just so it's shorter. So this would be ax I hat plus ay j hat dot bx I hat plus by j hat. And if these were three-dimensional vectors, you would have k hats and az and bz, but this should get the point across. And then you can just FOIL, right? Do the normal thing that you would do. You would first do these terms because it distributes, so it'd be ax I hat dot bx I hat, and that's just ax times bx because I hat dot I hat is 1. And then you would do these two terms, ax I hat dot by j hat. That would be ax by times I hat dot j hat, but that's 0, so those two terms would vanish, and so on and so forth, and you'd end up with 0 cross terms. You just get ax bx plus ay by. That is the scalar product written in components, and you would have an az bz if these were three-dimensional. So this is a way to just get the dot product without having to actually worry about angles and so on, or magnitudes. You just figure out the components, and then you just multiply across and add. This is easy and nice. All right, now, at the beginning of this, I said something like, there are 2 unique ways to multiply vectors in 3 dimensions. This first way is the unique way. It's the only well-defined way to take 2 vectors and multiply them together to get a scalar, to get a number out. Because keep in mind, this is just a number. It's like 6 meters per second or 19 feet or something like that. It's just a number. It doesn't have a direction associated with it. It tells you how much of the first vector was in the direction of the second vector, and then multiply those amounts together. There's another way of multiplying vectors, though, and this is called the vector product. And it has another name that we'll get to in a minute. So this is the second unique way to multiply vectors. And so unlike the scalar product, the vector product spits out another vector. So if you take the vector product of 2 vectors, your answer is a third vector. It's not just a scalar, it's not just a number. So just think back to the scalar product when we were talking about that 10 minutes ago. The scalar product relied on the component of one vector that's parallel to the other vector, right? It relies on the parallel parts of the vector. So if those 2 vectors are exactly parallel, you just multiply the magnitudes. And if those vectors are perpendicular, like I hat and j hat, then you get nothing. So it relies on how parallel the 2 vectors are. This vector product instead spits out, this vector product involves the perpendicular parts of 2 vectors. Yes, it is called the cross product because of the notation that's used. So if you have 2 vectors, say A and B, then the part that matters here will be this part. the part of A that is perpendicular to B. And so it will give you, so this value of A sine theta plays a role. Yes, dot product only yields a scalar value. So why can't we just say that you just take the perpendicular part of A, which is A sine theta, and multiply it by the length of B? Well, I mean, you could, but it wouldn't be well defined in 3 dimensions. And the reason I say that is because there's in 3 dimensions, there's a whole bunch of different ways that a vector can be perpendicular to another vector, right? It could be perpendicular because one of them's x and one of them's y, or it could be perpendicular because one of them's x and one of them's z. In which case, you kind of need to account for that. Otherwise, you get the same answer for two operations that should represent different things. So that extra information about the direction in which A is perpendicular to B, that extra information is encapsulated by the direction of the resulting product vector. So the magnitude will just involve the perpendicular length and the length of the second vector, but the direction of the resulting product encapsulates what direction that the first vector was perpendicular to the second vector in. So the extra information encapsulated by the direction of the resulting product vector. So what's the magnitude of this vector? So turns out there's a neat geometric fact. So if you just use some trigonometry, A times sine of theta is equal to this distance here, which is the amount of A that is perpendicular to B, right? So this tells us, like, if A was parallel to B, then that length would be 0, because the sine of 0 degrees is 0. If A was actually perpendicular to B, it would just be the length of A. So this just tells us how perpendicular A is to B. So, right, so the magnitude of this product vector is the area of a parallelogram, which is surprising, perhaps. So if you take a vector A, and then you add to it the vector B, right? This would give you a vector A plus B. But you could also do another thing. You could draw a parallelogram formed by those 2 vectors, where this angle here, that angle's theta, which is the same as that angle theta. So the area inside is equal to the magnitude of A cross B. That's the notation that we use. And that's the language I'll use. And so you could actually go home, do your geometry homework, and check that this is equal to A, the magnitude of A, times the magnitude of B, times the sine of the angle theta. And so that is just how perpendicular A is to B times the length of B. So that tells us that the magnitude is basically the same as the dot product. Like how you compute the magnitude is basically the same. It's just instead of taking the parallel part, you take the perpendicular part instead. So that's why this becomes sine instead of cosine. Just as an aside, the notation that we use is the standard x. It's the standard x between 2 vectors to give us this. That's the equivalent of the dot that we would use for the dot product. And so hence we call this type of product, rather than the vector product, we call it the cross product, because it's a little cross inside there. So now the question is, what direction does it point? We know it's a vector, so it has a direction and a magnitude. We already know how to find the magnitude. It's just the magnitude of A times the magnitude of B times the sine of the angle between them. But the direction goes back to this parallelogram. So A cross B, the picture you would draw, would be you take A, then you stick B to the head of A, and then you could complete this parallelogram by circulating. And so the direction that it circulates in that circulation direction of the parallelogram is relevant. Right, because, for example, if, you now have to think a little bit in 3D, but if in this picture, this circulation is counterclockwise in the page, right? But if instead, if A was pointing into the page, if we rotated this whole picture by 90 degrees, the circulation would not be in the page, it would be into and out of the page in a certain clockwise direction viewed from above. And so the circulation direction of the parallelogram that you form by composing A and B, that tells us something about the orientation of the two vectors A and B, which will tell us in what direction A was perpendicular to B in. That's the important part. So the way that we make this concrete, because so far this is just kind of an abstract think about parallelograms and things, is we have this thing called the right-hand rule. Now I think that I have to hold up my left hand in order for it to look like a right hand for you guys, right? So this is my left hand right now. Does it look like my right hand? Okay, it looks like my right hand. So for the rest of this course, I have to use the left-hand rule. That's always hard for me to keep in mind. Yeah, you're right. It's not commutative, and we'll get to that in a minute. So the right-hand rule is how we determine the direction of a cross product. So what you do is you curl the fingers of the right hand, and it's importantly, it has to be your right hand, in the direction of circulation. And then your thumb points in the direction of the resulting vector. So let me do this procedure for A and B here. So I curl my finger, so take my right hand, my left hand, the right hand for you guys. I curl it in the direction of the circulation. It circulates going around this way, right? So I curl my fingers this way. My thumb, in this case, is pointing towards me. Towards me. So that means that it would be pointing out of the, oh, so this is awfully confusing now, because from my perspective, oh, no, that's correct. So I'm using my left hand because I have to. So the resulting vector points into the page. And I've made sure that the perspective lines up and it works out correctly. So you guys should take your right hand and do this thing and see if it agrees with me. And if it agrees, then that's all we need to do in order for everybody to agree on the associated direction. So indeed, this is how we go from two vectors that are perpendicular in such a way. All we do is you just take your hand, you stick your hand in the direction of the first vector, A. I think I already do see how you see me. But I'll look into that. So you stick your hand, the easiest way to do this without thinking of a parallelogram, stick your hand in the direction of the first vector. So in this case, stick my hand in the direction of A. Then I curl my fingers so that they point in the direction of B. Then my thumb sticks out, and that's the direction of A cross B. And if B was into the page, say, so I would stick my hand in the direction of A, that's still the direction of A. But if B was into the page, I would curl my fingers into the page. So I'd have to rotate my hand to do that. So you'll have to do this to figure out what orientation does your hand have to be in so that your hand can point in the direction of A and curl in the direction of B. So if B was into the page, then the vector would be pointing down and to the right. But in this case, it's just pointing into the page. Right, so that takes us all the way through to the end, to 1150. I will talk about the properties of the cross product on Monday. And then we should be able to finish up all of this material that I wanted to. I think we only have, yeah, so we should be able to get, yeah, there's only like 3 or 4 more pages of notes that I need to get through for the homework to be doable, or for the homework to be completable, rather. So on Monday, you'll see the rest of the stuff, which includes the last problem, which is kind of involved, but we'll get there. All right, so I'm going to stop recording here.